So thank you. And I would like to discuss a very brief idea, which is centered around one of the main problems that is being discussed in the complex diffusion field. So as we have just learned, whenever you are studying complex diffusion in macroscopic systems such as birds, you can rely on experimental data that give you higher order moments. But when you are dealing with microscopic particles in a complex fluid, usually you rely just on two experimental quantities that are easy to measure, which are the mean square displacement and the displacement distribution. So one of the problems is that we have a plethora of models that are able to describe, such as that, the same qualitative behavior. So we have to discriminate which is the microscopic origin giving rise to a specific set of data. So this is a very important problem for the complex diffusion community, and they're also holding a competition, which is called the anomalous diffusion competition. And what they're finding is that the machine learning based models are consistently winning the competition, but also it's very difficult to define the origin of the anomalies when it is due to static heterogeneities. So for this reason, the question might be, is there any other experimental quantity that might be easy to derive that might come to help to these machine learning based models to detect the microscopic origin of the anomalies? And the answer is that we might call in to help an old friend of Brownian motion, which is fluctuation-dissipation theory in a global effective form. So you just need to perform two simple experiments. One is pre-diffusion to derive the effective diffusion coefficient. In the other one, you pull the particle, and from the settling velocity, you derive the effective friction factor. And what we show in a representative example here is that different models respond differently to the effective fluctuation dissipation relation, in the meaning that some of them hold the relation, some other fail to hold the relation. And so this is, of course, is not enough to distinguish between different microscopic origins, but we believe that it might be a side help as a side test to machine learning based models. And also very briefly, I would like to add that maybe the multi-fidelity models that we have learned about yesterday might be very game-changing in this kind of analysis. And also in my poster, I discuss a bit more in detail a generic setting that I'm developing, which we call the hydromechanic approach to complex diffusion. So that's it. Thank you.